Section 2.5. Solving not systems of equations. That's what we've been doing pretty much the first part of this chapter. Even though there were matrices involved, we used them to solve systems of equations. This is inequalities. And really, remember in equations, graphing was normally the least accurate unless you had a calculator. And here, graphing is actually the best because there normally isn't just one answer to a system of inequalities. There's a ton of them. And so it will show you where those possible answers are. And actually, once you get really good at it, it narrows it down even more. Okay? And so let's take a look at this one. So obviously, these are inequalities because of the symbols that you see in there. Because basically, that doesn't mean, it means not necessarily equal to. For example, the one on the left, if you had to read that, you would say y is greater than x plus 5, and the other one is y is less than x minus 2. Now realize there are a lot of symbols that could be used. Obviously, that's a symbol you can use. You can use that one, this one, and another inequality that you don't see a lot, that one. But that basically means not equal, just flat out. All right, that's what the last one means. And so this one obviously is just less than, that one is just greater than. Here's less than or equal to, and that's greater than or equal to. But you have to keep in mind that does change how we deal with these inequalities. So the first thing you're going to want to do when you have inequalities is, it's a helpful way to do it is to change the inequality to an equal sign. That's not forever. That's just so that you can get a graph. That's just so you can find out where is that. I call them boundary lines. Right? And so y equals x plus 5 and y equals x minus 2, I'm really hoping at this point you can graph those relatively quickly because they are lines. Right? This one right here has a y because it's really that form. The slope-intercept is 5. The slope is 1. So what that means is go to a y-intercept of 5. So 1, 2, 3, 4, 5. Put a dot there. And from there, remember, if the slope is 1, it's change in y over change in x. It'd be 1 over 1, right? So up 1 over 1. Now, don't get too far ahead of me, and I hope you're not using pen. Okay? Because this particular one has to be dashed. Now, can anybody give me a really good reason as to why it needs to be dashed? Yeah. Right. Basically, if I pick any point on that line and pick any one you want, what's the one we use? We use 0, 5, right? If I put 0, 5 in here, does it make it true? Does 0, 5 make that true? Back in the original? No. Because it would be, say, 5 is greater than 5. Does that make it true? No, it doesn't. Because I basically put 0 in there and 5 in there. It doesn't make the original true, which is why we make it a dashed line. If it's a solid line, you're saying all these points on here do make it true, but they don't. But that's still a boundary line. And then what you want to do once you get your boundary line is pick either above it or below it and find out, are the answers above it or are they below it? And you can pick any point you want as long as it's not on that boundary line. And so what's the most obvious choice for this one? 0, 0. Yeah, choose 0, 0 whenever possible. And what was the only stipulation I had? The point just can't be where? On that boundary line itself. So are you going to be able to use 0, 0 a lot? Yeah, probably quite a bit. So you try 0, 0. If I put that in there, again, notice that I'm going back to the original for this. So it'd be 0 is greater than, if I put 0 in there, what do I get? I get 5. Is that true? No, so you're telling me I tried 0, 0, and basically it failed, right? It didn't work. So should I shade below that dashed line that I have there? No, you shade above. And it doesn't have to be anything spectacular. Some people just use lines. Some really get in there and shade, and some get the colored pencils and shade. That's completely up to you. So any questions how I got that first boundary line in there? Well, unfortunately, this is a system of inequalities, meaning I'm going to have more than one. Okay, this one only has 2, so that's kind of nice. And so we got to go graph this other one. And the y-intercept on this one is -2. So you go to -2 and you start right there, right? And the slope is once again 1, so it's the same as up here. So you'd go up 1 over 1, up 1 over, and you keep going. And in other words, you'd get, well, let's get that to go away, I guess. You'd get that. Whoops. Oh, well. Wasn't supposed to hit that, but that's okay. So there's another boundary line. And again, why is it dashed? Because none of those points are actually going to make the inequality true. Okay? Got it? Okay. So again, it's dashed. A lot of people say, oh, it's because there's no equal to underneath. But it's really because those points don't make it true. But now, can we use 0, 0 again as a test point, even though it failed earlier? Yeah, we're testing it on a different boundary line now. So we can use it again. And how about 0, 0 this time? Again, go back to the original. 0 less than negative 2. Does everybody see how I got negative 2 there? 0 minus 2? Is that true? It fails again. Well, 0, 0 is not doing a very good job today. But, so you shade away. When you do a system, well, when you did a system of equations, you wanted to find out where the two were the same, right? Where they hit each other. Well, same thing here. You want to find out where do the two hit each other. And so where do those two hit each other? Yeah, they don't. So basically, as it says right down there at the bottom, which I wasn't supposed to hit, this system has no ordered pairs in common. Do you agree with that? There's no shading that overlaps, in other words. And so basically, what's the answer to this system of inequalities? Really unfortunate, after doing all that work, no solution. There's none that work for both of them. Am I going to do that to you very often? No. But I needed to make the point here that you're looking for where they overlap. So now it says, but many systems do have a lot of ordered pairs in common. And some of them even have what's called a polygonal convex set. That sounds really elaborate, but it's not. It basically means that it's going to be a convex polygon where they all shade together. That's all it means. Remember, convex just means it doesn't cave in. Okay, so that's nothing all that elaborate. It sounds kind of cool, though, when you say it. All right. A lot of people struggle on this one for some reason. Well, what was my first step back here anyways? What did I do first? Basically, just pretend for a while. Let's just pretend they're equals, right? So x equals 0. We need to graph that, right? So the question is, where does x equal 0? Well, does x equal 0 right there? Okay. Does x equal 0 over here? No, y equals 0. X equals what over there? 3, right? Does x equal 0 right there? How about up here? Over here? Okay. So all the places, basically you're looking for all the places where if you looked at all the ordered pairs, the x value would be 0. Otherwise known as the y-axis, right? Uh-oh, wait a minute. That one's solid. Why is that one solid? Yes? Oh. Yep. Do you agree? If I pick any point in there, does it make that first inequality true? Yes. 0, 0. Put it in there. You can only put in x. So 0 greater than or equal to 0. Yeah, it works. All right. So the second one will go, I don't agree. Here we go. Y equals 0. So does y equal 0 here as well? Yep. How about over here? That's the point I did last time, right? It does. And then how about here? No, it doesn't. That y doesn't equal 0 there. How about over here? No. Over here? Yeah. Okay. So in other words, y equaling 0, whoops, is right there. Once again, solid. Now you might wonder, isn't he supposed to be shading? Well, normally when I see those two, and you're going to see them a lot, I shade both of them, and then I figure out where do they shade together. Because otherwise I got too many shadings going on all over the place, right? So I like to get those two in there first. There they are. They're in there. And so I hope this one's easier than having to pick points. Where is x greater than 0 and y greater than 0? We normally call that what? Quadrant 1, right? That x is greater than 0, meaning positive. Y is greater than 0, right? So far, do you agree that basically we've eliminated here, we've eliminated there, and eliminated there, right? We're only looking quadrant 1, okay? So you can shade if you want, but you'd be shading like this, and then shading over here, and that's where they'd overlap, all right? Now we've got one more to do. X plus y, remember you're going to pretend, equals 5. An easy way to do these is just a nice little XY table. Whenever they're in standard form, I always like to try these. Because let's face it, what's the easiest number to substitute into something? 0. So let's substitute it in for x, and let's substitute it in for y as well. So if I put a 0 in there for x, well, what does y have to be? 5. Okay. So what if I turn around and do the second one, though, and put 0 in for y instead? Well, then X equals 5. You see that? How easy that is? So 0, 5. So 0, 1, 2, 3, 4, 5's right there. And 1, 2, 3, 4, 5's right there, right? So I'm saying there should be a line that connects those two, right? Should I make that solid or dashed? Solid, because let's face it, we know these 2 points make it work. We just proved that. We could put them in there, and it would be 0 plus 5, so that's 5, is less than or equal to 5. That's true. Okay, so solid, you tell me. Okay. I'll go with that. There it is. Looks like I missed a little bit with that one line, but close enough. Now we got to decide which way to shade. We know so far it's the first quadrant, so now we have to figure out above or below this line. Can I try 0, 0? If I'm basing it off of this slanting line, can I try 0, 0? I can. Is it okay that the other two are hitting 0, 0? It's fine. I'm just trying to decide just that line. So let's go ahead, try 0, 0. So 0 plus 0 less than or equal to 5, well, is 0 less than or equal to 5. So we know so far that it has to be first quadrant, right? So the only thing that really is left over is, I kind of sliced the first quadrant into 2 pieces, right? The outer part and the inner part there of that triangle. Is that a convex polygon? It is. There's your polygonal convex set. There it is. It's saying all of these lines. And seeing these are solid, it means truly all of these points are answers to that system of inequalities. Every single one of them. But here it is asking for the vertices. And they're asking for the vertices for a reason. How many vertices does this one have? 3. And so what are those vertices? Well, here's one of them, right? 0, 0. All right. There's one way up here, right, that we had black there for a second. 0, 5, right? And what's the final one? 5, 0. Okay. Again, there's a reason you have to find those. Really, right now, do you see any reason for it? No, it makes a nice triangle, but that's about it. Okay. Yes? Technically, it's whether the points on that line make the inequality true or not. If you want a nice, slick, and easy way of kind of cheating, if you trust your lines you draw, if the equal to is on the inequality, then make it solid. If it's not, it'd be dashed because those points actually won't make it true. Where here, 0, 5, if I put it in there, it makes the inequality true. Okay? But I want you to leave here not with just that idea, but actually why that is. Okay? All right. We got 4 of them. Well, you see 2 common ones, right? You see 2 common ones. So here we go. According to the vertex theorem, to locate maximums and minimums, all we need to check are the vertices. Because imagine if we had to check them all. You'd never be done. If you had to check all of them in that triangle, you would never be done. Because there could always be a point a little bit smaller than the one that you just tried. Right? And so you'd never be done. So that's why we find those vertices. Well, let's face it. X equals 0 is right there. Y equals 0. Right there. Right? I mean, isn't that what that does? And again, they're both greater than or equal to 0. So where, once again, are we kind of constrained at this point? Quadrant 1, right? It's basically, again, you could shade way up here and you could shade all of this. But really, we're saying it's not over here, and not over there. Now, is it okay if to graph my other lines, I put some points over there? Well, yeah, that's fine. But basically, we've taken care of those 2. Okay? So I would like you to take a second or 2 here and try and get those next 2 lines in there. Again, please use pencil in case you do mess up. And was I correct to make them solid? Yeah. So go ahead and try and get those 2 right now. Probably a little XY table is the quickest way, so get that done. Okay, here we go. Let's see how you did. Hopefully good. Look like people about half and half. You know, some of you are doing real good, some not as good. Well, I would do it this way. Put 0 in for x. Then what does y have to be? Again, you're pretending it's an equals. 4. If you put 0 in for y, it's got to be 2. All right, so 2, 0, and 0, 4, right? Solid or dashed? Hit the wrong one. Get out of there. Go away. There it is. I knew I was going to get close. So obviously there's your other line, but let's make sure our points are right. So on this one, if you do it like this, it'd be 0, 3, and 3, 0. And is that where I actually graph those? I did. So doing pretty good. Now you could take a guess, and it would only be a guess, but you could take a kind of pretty good guess that it's in here, right? But isn't this also kind of a convex polygon, these little triangles that it made? So it's possible, highly unlikely, but it is possible, so you should really check. And so this line right here, maybe I'll call it number 1, is right there, right? And we'll call this other one number 2, is right there. Can you test 0, 0 for both of them? Yeah. And you test 0, 0 on here, so basically a 0 and a 0, let's get rid of that stuff right there, is 0 less than or equal to 4? It is. So from that one, you would shade down, right? But you agree it still could be in that little triangle up there then. Okay, so we got to try the other one. And if we shade down from the other one, then we know that it's this little quadrilateral there. And so try 0, 0 again. Is 0 plus 0 less than or equal to 3? It is. So we're shading down from both of them. We're shading up from these other two lines. And so it does end up being there. Okay? And it is a quadrilateral, which we probably fairly expected seeing there were 4 inequalities. Right? But now, can I erase these tables, or is people writing those? Erase them? Okay. We're really not done with the problem, because it is said here, determine the max and min for that function. Did I try and graph that function at any point? No. Now, what we have are some ordered pairs there. This one right here is 0, 0. This one right here, we just had it up there, is 2, 0. That one right there is, careful, 0, 3. That last one always seems to be kind of the tricky one. But do you agree that that point right there better work in lines 1 and 2? Isn't that the whole system of equation things that we were doing at the beginning of this chapter? So do you agree, what is that, 1, 2? Does 1, 2 work in both of them, making it equal, right? 1, 2, yep. 1, 2, yep. So 1, 2 works. Okay, that's one way of always checking that last one to make sure you got it right. Let's say your graph was horrible. Well, you could just do a system of equations there and find it. So those are the vertices, correct? The beautiful part is that to find a max and min, I don't have to try all of these. Right, you'd be there all day. We know that the max and min happen at one of those 4 points. Well, the max happens at one and min at the other, more than likely. And all you have to do is substitute them in. So wherever I see an x, see, I'm going to try 0, 0. So wherever I see an x, I'm going to put 0. Wherever I see y, I'm going to put, well, when you do that, what do you get? You put a 0 there, you put a 0 there, you get 1. Should I do the same thing to get 2, 0? Well, similar, but not exactly the same, right? What you're going to do is for x's, you're going to put in 2. So right there, I'm going to put a 2. And right here, I'm going to put 0. So the end answer is 2 plus 0 plus 1, which is 3. Zero, 3. 0 in for x. 3 in there makes it a 6. So 7. And well, it doesn't matter what order you do them. Yeah. 1, 2. So you put 1 in there, you put 2 there, makes it a 4. So you get 6. Now you might wonder, where is this used? It's actually used a lot in production, believe it or not. But so is statistics. Well, you know, take that class if you want to see how that's used in production. So what's the max? 7 at 0, 3. You should say 7 at 0, 3 is the max, right? Does it ask for both or no? Yep, min is 1 at 0, 0. Question? Yes. Oh, the big black ones. Okay. I looked at these first two that I circled in black here. X is greater than or equal to 0 and y is greater than or equal to 0. I see those so much that I know this is x equals 0, this vertical one, y equals 0, this horizontal one, and x greater, that means x being positive, which is this way to the right, and y being positive means up. And so it really eliminates it to the first quadrant at that point. And so when you see those two, you can kind of just think first quadrant if you want. Now if those change a little bit, like x greater than or equal to 2 and y greater than or equal to -7, well then you might want to go put those lines in and find out where is that. Okay? But for right now, you see those two, that means first quadrant. Okay? And for most of what we're going to do, it's going to be real life problems, and that's where they're going to be, first quadrant. Okay?